Welcome back to our series on multivariable calculus. In this episode, we're going to look at the fundamental theorem of line integrals. It's based very closely on the fundamental theorem of calculus, which you learned last year in Calculus 2. Here's the basis of the fundamental theorem of calculus. It says if I take the integral from a to b of f prime of x dx, then I can evaluate this integral of this function by just evaluating it at its endpoints. But I'm not evaluating the function we're taking the integral of. We're going to do the antiderivative of the function we're taking the integral of. This sort of defined the whole idea of antiderivatives for us and its purpose. To find the area under the curve of a function, we had to integrate it. We had to find out the function whose derivative was being analyzed. And of course, the answer is we just analyze the function at its two endpoints. And if we analyze it at its endpoints, that will take care of the value of the integral. Well, think of applying this to the line integrals that we have been working on. Well, those line integrals have also dealt with derivatives, but of course, they're multidimensional. They're not just functions of x. They're functions of x and y, and sometimes functions of z as well. That means their derivative isn't so much their derivative as the set of partial derivatives. And of course, we know what a set of partial derivatives looks like. The best way to represent that is with a gradient. And so the fundamental theorem of line integrals begins with the idea that I'm going to take the integral over a curve of del f. In other words, what we're dealing with is the partial derivative. So del f dotted with dr. This looks a lot like the functions we've been working with lately. In particular, it's the dot product between these two vectors, where del f is going to represent a vector field, and then dr is the path through that field we want to take. And we're interested in the degree to which this vector field points in the direction of the path. Well, as you might expect, we can evaluate this by first figuring out what's the antiderivative, or in this case, the antigradient of the function inside. What if del f is what we're integrating, what's f itself? And of course, the answer is it's going to be f of b minus f of a. That is, if I can evaluate f, which is the antigradient of the function we're integrating, at its endpoints, and that's assuming that's the endpoints of the curve described by dr. Now, look at the value of this. Sometimes dr is a really complex curve within the plane. And of course, the integral depends intimately on our ability to express this either as a function of x and y or as a parametric function of t. And it's really going to control the difficulty of what the integrand looks like. And basically, what the fundamental theorem of line integration says is we can ignore that path completely. We can instead just look at the endpoints of the path and treat it as if this function moves in any path between a and b, basically assuming that the value of the integral will be the same regardless of path. That is a really powerful statement, but it comes with a couple of caveats. First, we're modeling this as if it's a foregone conclusion that the function under the integral is the gradient of another function, and that's not necessarily true. As a matter of fact, it's the first thing we have to test for. If you want to apply the fundamental theorem of line integrals, you have to go through a process. The first thing we have to check is if there is a function f that this represents the gradient of. Just because the integral is represented as a gradient doesn't mean every integral we're provided with can be solved by the fundamental theorem of line integrals. So the first thing we need to check is del f. We know that's going to be a vector composed of the partial derivatives of this theoretical function f. Well, in order for these to truly represent a gradient, I know something about the first and second partials of a function, namely that the two cross partials have to be the same. That is, the cross partial of fxy must be the same as fyx. So that's the first thing we do, is check that. So step one is check, is fxy equal to fyx? If the answer to this is yes, that it checks out, then you can apply the fundamental theorem of line integrals in order to solve this integral. But if the answer is no, then it's full stop. You'll have to go back and try another technique. You'll have to handle this like we do every other line integral, because it basically means the fundamental theorem won't apply. If fyx is not equal to fxy, then in fact, the function indicated that you're integrating is not the gradient of another function. But if it is, and the answer to this is yes, we can head on to step 2. And step 2 is to find the original function that this is the gradient of. We're going to learn how to do an antigradient. Step 2. Assuming such a gradient exists, we want to now perform the antigradient. And how do you perform an antigradient? Well, we can start with either partial. I'll start with the partial with respect to x. So what we want to do is reform the original function f by integrating the partial of x with respect to x. In other words, we're going to take this and integrate it with respect to x. Now, keep in mind, fx could be a multi-dimensional function, that it's going to have x's and y's. So we're really sort of performing a partial integral. We're going to integrate with respect to x and leave the y value constant. Of course, if I want to reform the original f by basically undifferentiating the partial with respect to x, the process that turned f into its partial with respect to x would have ignored any y function. It would have treated it as a constant, and it would have basically differentiated it out. So I need to add on to this the potential that there was a gy, part of our original f, that the partial with respect to x deleted. It basically integrated it away. Okay, so this then is going to form our basis for our antigradient. We're not done yet though. All I've done is formed what could potentially be the f. That is, it'll be the antiderivative of the partial with respect to x plus an unknown function g of y. How do we go about finding that unknown function? Well, here's where the magic comes in. I'm going to take this function that I just formed, and I'm going to take its partial with respect to y. When I do that, that will mean the partial with respect to y of whatever the result of this integral is. So the partial with respect to x dx. And then, of course, if I take the partial with respect to y of a function that is exclusively a function of y, that's just the derivative with respect to y. So that would form g prime of y. So I've taken and formed my potential f by integrating the partial with respect to x, and then I take the answer to that and I take the partial with respect to y. Well, the good news is we actually know what the partial with respect to y of this f is. It's sitting right here. So our next step is to do a comparative analysis. I'm going to set this equal to fy, the partial with respect to y, which was contained in the original derivative, or the original integral. Well, now what I'm going to be able to do is function match. Much of this will look exactly like portions of this partial, but there'll be some things left over. And the leftovers are going to solve for me the problem of what is g prime of y. G prime of y will then be known. I'll be able to identify exactly what that is by comparing it to the partial with respect to y. And then what do? Well, I go ahead and integrate that with respect to y, and that will reform my g of y function. When I'm done getting g of y, then I finally know what f is. F will be equal to the integral of the partial with respect to x dx plus the gy that I just solved for. And the good news is when you're all done, you can very rapidly take the fx and fy partials. That is, you can take the gradient of your final answer and see that it actually produces the gradient that were contained in your original integral. If this function exists, then the answer to this integral is simply to take the endpoints of the curve, ignoring the path, and evaluate f of b minus f of a, and that will give you the answer to this integral. Keep in mind, this is not a universal process. Not every line integral can utilize the fundamental theorem of line integrals, because not every line integral is representative of the gradient of another function. But any line integral that is the gradient of another function, this amazingly powerful shortcut is at your fingertips. All you have to do is practice a few times going through the process of the antigradient.